in P3.
Thank you very much, and again, thanks to organizers for giving me this opportunity. It will be a talk on integrable maps, and this is one of the areas which Sasha shaped absolutely. And I think his review paper with this same title in Uspekhi is an indispensable reference and the standard reference for everything in this area. So this will be about special kind of integrable maps, discrete Painlevé equations, which we have heard already in this day. And what I would like to propose here is a different geometric interpretation of these maps with the help of objects which are somehow, I would say, slightly unexpected in this context. I believe that nobody have seen pencil of quadrics in this theory, and this is what it will be about. But in order to start, I have to quickly maybe give an explanation of what discrete Painlevé equations are, because there are specialists here in this audience, but the non-specialists are somehow hesitant to understand what Sakai theory is about because of heavy formalism there. And actually, I would like to argue that the theory is very simple and easy to understand on the top level. So on the level of the most generic discrete Painlevé equations, because there are one doesn't have to deal with discrete Alfang surfaces. So those blow-ups of P2 at 9 points. If these 9 points are all different, then you can think of them just as of 9 points. Yeah, and this is what I will quickly explain. So on the top discrete Painlevé equations, you are dealing just with configurations of 9 plus 1 of 10 ordered points in P2. So you factor out the three symmetry of projective maps on the space of homogeneous coordinates. You factor out the corresponding factor, and you consider the first 9 points as the parameter of your map, and the ninth point as the dependent variable, so the object to which you iterate. And then you introduce the action of the affine Weil group on this modular space by rational maps which move the parameters and the dependent variable. And they move them in a very simple way. So everything is generated by well, nine roots, by 9 maps, and 8 of them are extremely simple. They just swap the two of the points of the parameter points and do nothing with the last column of this matrix. And the one non-trivial thing is the root S0, which is also of a very simple geometric origin. It is just the Cremona inversion based at the first 3 points. So let me quickly remind you what the Cremona inversion is. You just normalize by means of GL3 the first 3 points to 1, 0, 0, 0, 1, 0, and 0, 0, 1. Then you have still a freedom of to fix the image of the 4th point. You fix it to 1, 1, 1, and then what the map maps does with all other points, with the last parameter points and with the dependent variables, is x, y, z to 1 over x, 1 over y, and y of 1 over z. So that's all. And these Cremona inversions applied actually to all possible triples of base points generate for you the action of the affine Weil group E81.
Excuse me, but weight triples, you use 4.
Sorry?
You use
This is just a normalization. Yeah. Based on these points in the normalization, which takes the 4th point to 1, 1, 1. There is slightly more freedom here. Indeed, four points are involved. Yeah, and this is an infinite group of birational transformations, of Cremona transformations, which reg the parameter points as well. And among elements of these groups, there are translations, and these translations are just the discrete Painlevé equations. So nothing more than that. This is for generic 9 points in the plane. And generic 9 points in the plane define uniquely a smooth cubic curve. And if this cubic curve degenerates in some way or another, you will get all the tower of degenerations in the Sakai table. I show you the beginning of the table in P1 cross P1 formulation rather than in P2 formulation. So one can do the stuff also in this birationally equivalent picture in P1 cross P1, and this will be slightly more convenient for me for the later goals. So on the top left, you see the 8 generic points in P1 cross P1, which support generic biquadratic curve. And then you can have this biquadratic curve, a nodal curve or a cuspidal curve. These two will be rational, or it can cease to be irreducible. It starts to consist of several components, 2 components here, 3 components here, 4 components there, and so on. And this is the first place where the picture becomes slightly more demanding analytically, because there are infinitely near points, and this makes the picture complicated. As soon as you have 8 distinct points, you don't need a lot of algebraic geometry for this. This is just P1 cross P1 with a choice of 8. Okay, and these are the discrete Painlevé equations for which I would like to give a new geometric interpretation. Before doing this, and just to introduce the way how these came to existence, let me consider in detail one simple example, the so-called QP3 in old notation, in bad notation, I think sometimes called QP5 or QP6 or whatever. So this is this.
Maybe tell which element in the Sakai table it is, so that because otherwise.
This you will see this picture soon.
5.
Okay, so you have this non-autonomous difference equation of the second order, and the parameter Cn evolves in this exponential way. So this is the QRT recurrence, and it's in the early days of discrete Painlevé equations, it was understood just as a de-autonomization of the system where the parameter is constant. And this is an instance of the so-called QRT recurrence, actually a QRT, not a QRT map, but a QRT root, because its second iterate is what a QRT map is. I will remind you quickly what it all means. So let us start with the autonomous case. So C is a constant. We have a second order difference equation, which can be interpreted as a map of C2 to itself. Inverse map is given by almost the same formulas. They are just conjugated by swapping the arguments. If we compactify C2 to P1 cross P1, then we see that this map has 4 indeterminacy points where you have to divide 0 by 0, and the inverse map has 4 indeterminacy points, and this is the list of 8 points which sit on 4 lines, and so you see this picture from the Sakai table. And I would like to argue that actually these 8 points define for you everything. Yeah? So this is the data, the geometric data, which define the dynamics for you. So how to do this? These 8 points are in a special position. They support not just a unique biquadratic curve, but a pencil of biquadratic curves. This is the equation of the pencil. So this is one generic biquadratic, and another biquadratic is just the union of 4 lines here. Yeah, and it turns out that this map, and this was actually the starting point for the discovery of discrete Painlevé maps in the early days by Papa Georgio and Romanian Grammaticus, yes, the so-called singularity confinement criterion. The singularity confinement criterion is written here. So this is a birational map. It blows down 4 lines. Then the images of these 4 points are iterated once, and they land at indeterminacy points, so they get blown up again. So all critical curves which are blown down after several iterates become blown up again. So they land at indeterminacy points. And this is the crucial property of singularity confinement. It will be also quite important for me in the following. So how do you start how do you construct the map F starting from the geometric information? You for any generic point in P1 cross P1, you determine a unique curve from the pencil through this point. And on this unique biquadratic curve, you play the following game. You can either intersect this with the vertical line through your point, or with the horizontal line through your point. And this gives you each time a second intersection point. The biquadratic intersects horizontal and vertical lines twice, exactly twice. And this defines for you a vertical switch I1 and a horizontal switch I2. They are given by these formulas, and you see immediately that our QRT root is just the composition of any of these involutions with the interchanging of X and Y coordinates. So this is the so-called QRT root, the map S composed with I2 or composed with S, because the square of this map is just the composition of I1 and Y2, and this is the standard definition of the QRT map. So now, how do we de-autonomize this QRT map? So again, in the early days of the discrete equations, the requirement was that the singularity confinement property is preserved. And it turned out that this singles out the formula for the evolution of parameters. So this de-autonomized second order difference equation is still integrable. The question is in what sense. It is universally accepted as an integrable system, but it is not Liouville integrable. It does not have a rational or algebraic integral of motion. Actually, the integral of motion is transcendental, comes from isomonodromic interpretation of this system, but it has vanishing algebraic entropy and some other properties which are universally accepted as definitions of integrability. So what I would like to do next, somehow not very well motivated, I would like to consider a 3-dimensional map with a singularity confinement structure imitating that of QRT. Namely, it should have 4 planes which will be blown down to points, which will be iterated once and land at the indeterminacy points of the map. And it turns out that this can be done with this very simple ansatz. So we take just the 3-dimensional Cremona inversion and compose it with a linear map, with a linear projective map. And I will try to adjust the map A so that the singularity confinement property is satisfied. So the dynamical properties of Cremona inversion are very simple. It just blows down coordinate planes to vertices of the canonical tetrahedron. And since it is an involution, it blows up those points to coordinate planes. So the singularity confinement property is trivial and it has no dynamics. It is just an involution. But if we switch the linear map, then the dynamics becomes non-trivial. So it is clear that the coordinate planes will be mapped to 4 points, which are images of our points under A. The 4 points EI will be mapped to 4 planes. And now we're looking for the matrix A such that these points A are mapped to EI. Then we will have the singularity confinement patterns of exactly the same the same kind as for the QRT map. And this is just an equation for the coefficients of the matrix A, and this is more or less generic solution. So these are matrices which produce the maps with this singularity confinement rule. Now it turns out that for Q equal to 1, we just end up with an integrable map, namely this map for the matrix A with Q equal 1 will preserve a two-dimensional family of quadrics spanned by two pencils of quadrics with a common quadric Q naught. And so these are just the equations of these quadrics. So the map will have two rational integrals, each one a quotient of two quadratic forms. So this is an integrable map, but not only this, it turns out that this map is an instance of what we call a three-dimensional QRT map. So this is not obvious from the construction, but this can be established, and here is how it works. So we take any point on the quadric of the pencil. We compute the corresponding lambda, and then we draw the two straight line generators on this quadric of one of the pencils, of the pencil Q. It is useful to have the so-called pencil adapted coordinates in which the two straight line generators are just described by x constant or y constant. So this is the example of pencil adapted coordinates for this concrete pencil. And so the x and y small coordinates are given by these rational functions. And then one computes just the map in these pencil adapted coordinates, and this is what one gets. Yeah? So we are dealing with a map on P3. It is defined by three coordinates, and these three coordinates are x, y, and lambda. These are pencil adapted coordinates. Lambda is preserved. This is the property that the integral, the first integral is an integral, and the evolution of x and y variables is the same as for the two-dimensional QRT map, depending on the parameter lambda. So it is, so to say, a collection of QRT maps on each quadric of the pencil. And the parameter of this QRT map is just the parameter of the pencil. So each quadric Q lambda is invariant, and in pencil adapted coordinates, we just have a two-dimensional QRT map depending on the parameter lambda. And this was a very inspiring example, because if you you can formulate this in quite general terms. So this is the construction of the so-called QRT maps defined by two pencils of quadrics. You start with two pencils of quadrics, Q lambda and Q mi. So they will play different roles in the construction. And the game is the following. You take a point x, you consider the quadric Q lambda through this point, you determine lambda in the unique way. You consider two straight line generators of the quadric Q lambda through this point. And then you look for the second intersection points of this quadric with the corresponding quadric of the second pencil, P mu. So this is the definition of the two involutions, which we call 3D QRT involutions. And then you compose these two involutions and you get what we call 3D QRT map. And if there is additional symmetry there, then you can define a functional square root of it. And by construction, this map will be integral. In the Liouville sense, it will have two integrals, two rational integrals. One can prove that it has an invariant volume form. So this is a quite standard integrable map. If Q, this is the theorem, if Q is equal to 1, then our map defined by a composition of Cremona inversion with a constant matrix A is actually a 3D QRT root. So you see here the geometric illustration. So here is the initial point. Here is the quadric of the first pencil on which this game is played. This is the movement along the first generator and then the symmetry, or you can alternatively start with the symmetry and move along the second generator, and the answer will be the same. So this is the illustration how the QRT root acts. on each quadric of the first pencil, you run along the straight line generators till the intersection of this quadric with the quadric of the second pencil, which is a elliptic curve in space. Okay, what happens if we take the matrix A with Q not equal to 1? Then it turns out that the singularity confinement is preserved by construction. We have chosen the matrix A so that the singularity confinement is preserved. So we will have the same singularity confinement structure so that the map is expected to be integrable, but it is not integrable in the previous sense because it turns out that it does not preserve any quadric. The pencil P mu disappears altogether, and the pencil Q lambda continues to play an important role. It is a pencil of quadrics through our 8 points EI and AI. So now they support not a two-dimensional family of quadrics, but just a one-dimensional family of quadrics, a pencil Q lambda. But it doesn't preserve the quadrics of this pencil individually. So each quadric Q lambda is sent to the quadric with the parameter Q square lambda. So we travel along or across the pencil of quadrics. And in the pencil adapted coordinates, we have the following formulas. So the formulas for the evolution of X and Y are the old one, and the lambda is now not fixed, but is evolving in this exponential way. So in other words, the coordinates, so what we have got is nothing but this discrete Painlevé equation. Okay, and actually this was the inspiration to formulate the general recipe, which I would like to present now. So how to de-autonomize a given QRT map in an integrable way, leading to discrete Painlevé equations. So the input data, we have a pencil of biquadratic curves in P1 cross P1, what is the same 8 points in special position supporting a pencil. So as I explained, we can construct a QRT map out of them, and then we choose one biquadratic curve of this pencil. We just fix any one and declare it to the fiber along which we would like to de-autonomize. And what follows is the construction, the solution of this problem. So how to de-autonomize this, and the answer will be a three-dimensional, an autonomous three-dimensional map, which in a certain sense defines for you non-autonomous two-dimensional maps. And I will explain where do these maps live. So this is the goal, and this is the algorithm. So we start by interpreting our plane P1 cross P1 as a quadric in P3. It is a standard Segre embedding. This will be an important object, so the quadric given by this equation. And then we lift the base points from P1 cross P1 to P3 just by the same Segre map. Then the pencil of biquadratic curves is lifted to a pencil of quadrics in P3 by this prescription. So this is the one-to-one correspondence. So to each biquadratic curve, I put into the correspondence a quadric whose intersection with the Segre lift of P1 cross P1 is the biquadratic curve C mu. So I lift everything in P3. And then I construct a pencil of quadrics, Q lambda, which will play the main role in the story, as the pencil spanned by Q naught and our distinguished quadric. The quadric distinguished by the condition that it is a lift of the distinguished fiber of the pencil. So I take Q naught and I take P infinity, and I span a pencil of quadrics by these guys. Then I consider the 3D QRT involutions defined by these data, as I described in the previous part. This is the movement along generators of the pencil till intersections, second intersections with the corresponding P mu. So this is an integrable map. So this is this is, so to say, a integrable three-dimensional QRT map, which corresponds to our two-dimensional QRT map we started with. There is, however, a small problem at this point, that this map will not be birational in general. Why that? This is because the generators of the pencil of quadrics do not necessarily depend rationally on the point. Here you see the simplest example. So consider this pencil of quadrics. Then you compute the generators, you solve quadratic equation, and you get a square root of lambda here. So everything is rational functions for a given point in terms of coordinates of this point, but depends on the square root of lambda. But lambda is, of course, the x1 square plus x2 square plus x3 square in homogeneous coordinates, non-homogeneous coordinates. And therefore, everything depends on this square root of x1 square plus x2 square plus x3 square. It is not a rational function. So how to deal with this issue? So actually, this is the general statement. The generators are rational functions on x and of the square root of the polynomial of degree 4 in lambda, which is just a characteristic polynomial of the pencil of quadrics. So that means that if this characteristic polynomial is a full square, then we are happy, then all our maps are birational. If this characteristic polynomial is not a full square, then we have to deal with its square root somehow. Now it turns out that one can classify all pencils of quadrics in P3 over complex numbers, and there are 13 projective classes. And for 6 of them, the characteristic polynomial is not a complete square, and for 7 of them, it is. So here is the classification of pencils of quadrics in P3 over complex numbers. So this is the generic case. So the pencils are the same as the base curves of these pencils. So the first case is just a pencil through a generic curve of degree 4. And then there are several degenerate cases when this curve is nodal or cuspidal, and then this curve of degree 4 can split into two conics which intersect at 2 points, or two touching conics, or a double conic. And these are the 6 classes where the characteristic polynomial is not a complete square. And then there are 7 classes when this polynomial is a complete square. So if the base curve is a union of a twisted cubic and a line, a second line, or twisted cubic and its tangent line, or a union of a quadric of a conic and two lines, or they can also touch, or there is a pencil where the curve of degree 4 consists just of 4 lines, a skew quadrilateral, and one of the lines can be a double line, or two of the lines can be double lines. So these are all the cases where we have no problems, because the characteristic polynomial is full square. And let me continue with this case. So let us first consider the case where the characteristic polynomial of the pencil of quadrics is a complete square. Then we consider we would like now to deform this integrable QRT map to a discrete Painlevé map. In order to do this, we compose this with a map L, and the map L is a map, birational map on P3, which preserves the pencil, but not the quadrics of the pencil individually. So these are this is the main object, which we call the Painlevé deformation map. It would be a birational map which allow you to travel across the quadrics of the pencil. Here is a recipe for the construction of this map. fiber-wise formula for this map. And it is a general statement that the so defined map is birational. We will see that in many cases it's even a linear map, and that the compositions of this map with both 3D QRT involutions have the same singularity confinement properties as the original system. And so this composition is then called the 3D discrete Painlevé equation, which is obtained by construction by the de-autonomization of the QRT map along the fiber C infinity. I remind you, we lifted the fiber C infinity to the quadric P infinity and spent a pencil by the quadric Q naught and its P infinity. So everything starts and ends with the information about the quadric P infinity. So you don't need anything beside it. So, and the requirement is, the requirement is that the traveling across the pencil happens according to a Möbius transformation of the parameter lambda, which fixes the points where the quadrics are singular. So our pencil has two singular quadrics, and our Möbius transformation should fix the both lambdas. Yeah. So there are two cases, as we have seen, either there are 2 points lambda squared, we can normalize them to be 0 and infinity, and then the sigma of lambda is just the multiplication of lambda by a constant. Or if we have just 1 point, we can consider sigma of lambda as a shift fixing the infinity. And what is important and what differs the situation from the Sakai construction is that we can choose this Q and delta arbitrarily. So it is not dictated by the configuration of points. The configuration of points we started with has nothing to do with this parameter. This parameter is completely free. So here, let me give you just a quick list of examples. So here we start with a point configuration of this surface type. The corresponding picture in the space will be the pencil of quadrics spent with the base set being conic and two lines. This is the canonical equation for this pencil of quadrics. So the base curve consists of these two lines and the conic. The characteristic polynomial is immediately computed to be a square, which means that one of the points is at infinity and another one is at -1. It turns out that the map in this case is just linear projective map. And yeah, the corresponding map in coordinates will be just the Sakai's one of the discrete Painlevé equations from the Sakai list. I don't reproduce this equation explicitly, but it is just the equation from the list, and it corresponds to traveling between the quadrics of the pencil. So once again, the different generalized Alfvén surfaces on which between which the discrete Painlevé maps act are now realized as different quadrics of the pencil Q lambda. So this is the next case in the Sakai table where these three objects touch. Again, we compute the characteristic polynomial of the corresponding pencil. The polynomial is equal to 1, which means one quadruple point at infinity. And now we have additive Painlevé equation. This is the example I started with. So the corresponding pencil of quadrics is given here. It is its base set consists of a quadrilateral of a skew quadrilateral. These are the 4 lines. The characteristic polynomial is this one, which corresponds to 2 singular values of lambda at -1 at infinity. The corresponding equation is just the corresponding map L is again a linear map given here, and if we play the game, we get the equation I started with. An example with 2 pairs of infinitely near points, everything works well, and the map L is still a linear one. Another one. So I just do not go through the details of construction. You can just follow the recipe, and you will end up with discrete Painlevé equations from the Sakai paper. This is a slightly more complicated example, which for some reason was not listed in the Sakai paper explicitly, where the reason is because Sakai works in P2 and not in P1 cross P1, I think. The curve, biquadratic curve, consists of a horizontal generator of a horizontal line and a 2-1 curve, a parabola. So then the base curve of the pencil in space consists of a twisted cubic and one of its tangent line, as shown here. The characteristic polynomial is equal to 1, which means that we have a quadruple point in infinity. That means that we are dealing with a difference Painlevé equation, and the map L, the Painlevé deformation map, is just this map of degree 2 now. Okay, I think I have a couple of minutes left to discuss quickly the cases where characteristic polynomial is not a complete square. That means that we are dealing not with birational maps. We have to work with a Riemann surface of the square root of characteristic polynomial. It is always a double cover of P of a sphere branched at 4 points, or in some degenerate case at 2 points. Its universal covering is always C, and we have a holomorphic uniformization of this universal covering. And instead of P3, we work with a double cover of P3 branched along the 2 or 4 degenerate quadrics of the pencil. The recipe for the construction of the map L is very similar to the previous one, but now we just shift the uniformizing parameter by additively by delta. And then there is one further ingredient of the construction which was absent in the previous case. We have to factorize this map L into 2 maps depending in pencil adapted coordinates on coordinates in a triangular way. So the maps with the index L with the index 1 do not change the first argument, and the maps with the index 2 do not change the second argument. So this is how the corresponding maps act in pencil adapted coordinates, and it is easy to prove that any map L can be factorized into 2 such maps, triangular maps in one order or another order. And now we define the 3D Painlevé map in the following way. We deform the involutions, the QRT involutions I1 and I2, just by sandwiching them with the corresponding maps R1, L1, R2, and L2. And in general, one can prove that also for this map, the singularity confinement property is automatically satisfied, and we get the standard Painlevé equations here. There are, of course, 3 cases. The generic case where this polynomial, characteristic polynomial, has 4 different roots, and this is the case of Sakai's elliptic Painlevé equations. One of the periods of the corresponding torus can go to infinity. It will correspond to a cylinder instead of a torus, and this will correspond to cube Painlevé equations. Or both periods can go to infinity, and then we are dealing with difference Painlevé equations. And again, the parameter delta or q of the Painlevé equation does not depend on the original configuration of points. I have just want to give you formulas just to one simplest example here, just in order to see how it works. So this is the configuration of points on 2, 1, 1 curves. The corresponding base set in the space is 2 touching non-planar touching conics. This is the canonical form of the corresponding pencil. equations of the base curve, the lift of the base points. Characteristic polynomial is just a linear one, which corresponds to branching points, 1/4 and infinity. This is the uniformization of the square root of 1 minus 4 delta. The formulas for pencil adapted coordinates, they are holomorphic with respect to mu, to the uniformizing variable now, not with respect to lambda, so it contains square roots. These are the base points in the pencil adapted coordinates. We see that 4 of them do not change and 4 of them depend on nu. A quite important point is that these are the coordinates of the same points on different quadrics. So the points in the space do not move, do not change, but their coordinates on the quadrics do. And this is the origin of the non-autonomous property of discrete Painlevé equations. We are dealing with a fixed point configuration of coordinates on change in the travel across the pencil from one quadric. The formula for Painlevé diffraction map, which depends rationally on coordinates and on nu on the uniformizing variable. In the pencil adapted coordinates, this map looks quite simple. Factorization is also simple, and what you get at the end of the day is the corresponding discrete Painlevé equation from the Sakai list. So to finish, I would like to give you actually one reference, because the second paper is under writing yet. It's not finished yet for the branching case, for the case where the characteristic polynomial is not a full square. And maybe to underline once again the curious features of our construction, which are probably unexpected for specialists in discrete Painlevé equations. So we are dealing with 8 points in the space which do not move at all. So depending on the base curve also does not move. The base curve doesn't change. But what changes is the description of this curve and these points on different quadrics of the pencil. So if we travel across the pencil, the equations change, but the geometric images do not. Okay, I think I will stop here, and thank you for your attention, and congratulate Sasha.